Now students, now we'll see the difference between PCM, DPCM and this delta modulation. Now in PCM, what you are doing is all samples are transmitted, right? In PCM, all samples are transmitted. Now while you come to the DPCM, what you are doing is difference between present and previous or predicted one, right? Present sample and previous sample value. Difference between present sample and previous sample value. All samples are transmitted. Now this is X of NTS and X cap of NTS. Now here all samples, all X of NTS samples are transmitted. Now this is sampling, and this sample is going for quantization, encoding and decoding. But only this difference is going for quantization and going for encoding. Now in delta modulation and this DPCM, all are same. Now this is X of NTS minus X cap of NTS. Now this difference is going for sampling. Now this is X of NTS minus this is X cap of NTS. This difference is going for sampling. Now the question is, in delta modulation, now in this delta modulation, this is the difference. Now this X of NTS, which is greater than X cap of NTS, when this difference is greater than this, or when X of NTS, which is less than X cap of NTS, when this sample signal is greater than the reconstructed signal, or a sample signal is less than the reconstructed signal. If this greater than, this is plus delta, one quantization level, less than this is another quantization level minus delta. So both are same. When this difference is positive, which means that difference is positive plus delta, difference is negative minus delta. So let us take this DPCM delta modulation, all are same, everything is same, diagram and everything will be same, but this difference is positive, this is encoded as quantized as plus delta. This difference is negative, it is quantized as minus delta, which means that, so we call it as DPCM delta modulation is same. Now this delta modulation is also called as one bit DPCM system. This delta modulation is also called as one bit DPCM system. This delta modulation is also called as one bit DPCM system. Now this is delta modulation and this is DPCM, both are same, but this is one bit DPCM system. A one bit DPCM system is called as delta modulation. The delta modulation is also called as one bit DPCM system. Now see here, now what is the meaning of one bit? N bit means each sample is encoded into n bit. One bit means each sample is encoded into only one bit. That's why this difference is positive. This is quantized as plus delta and encoded as binary 1. Now this difference is negative, is quantized as minus delta and it is encoded as binary 0. Delta modulation is also called as 1-bit DPCM system. So DPCM system, delta modulation both are same, but here the encoder is, in delta modulation, encoder is n-bit A to D converter. Now in delta modulation, encoder is 1-bit A to D converter. Means each sample is encoded into only 1 bit, either binary 1 or binary 0. Here each sample is encoded into n bits. So what is the advantage of this, sir? Why you are doing like this? Then what is the advantage of this? If you are doing like this, now see here, now here this is the bitrate RB, which is equal to 1 by Ts into n bits per second. Now here bandwidth, which is equal to 1 by Ts into n hertz. Now this is also same, but the correlation, more number of samples which are correlated, therefore the quantization error is somewhat less. Now here a quantization error is more, here quantization error is less, but bitrate and bandwidth will be same. Now I want, so what is the final aim? Our final aim is to, minimize the quantization error. Our final aim is to minimize the quantization error. Quantization error is already decreased. Now noise is decreases. But now my intention is to decrease the bitrate and bandwidth. So in delta modulation, I am expecting less bitrate and bandwidth. So in delta modulation, we are expected bitrate and bandwidth is less. So what happened bitrate and bandwidth? Now let us see here. Here the encoder is n-bit A to D converter. Here is also encoder is n-bit A to D converter. But here encoder is 1-bit A to D converter. Now what about the bitrate here? The bitrate RB, which is equal to 1 by Ts into n is 1. So the bandwidth, which is equal to 1 by Ts into n is 1. So now this is RB, which is nothing but bitrate. This is 1 by Ts, which is equal to sampling rate. Now that is bitrate and this is sampling rate. Now in delta modulation, now this is bitrate, now which is nothing but sampling rate. So in delta modulation, bitrate and sampling rate both are same, is one point. Now what is the bitrate and bandwidth? Now here bitrate and bandwidth is sampling rate multiplied with some n, sampling rate multiplied with n. Now here what is only sampling rate multiplied with 1. Therefore in delta modulation, bitrate and bandwidth is decreased or not? Yes. Now the bandwidth is same. Now in delta modulation, bitrate and bandwidth is decreased. Bitrate and bandwidth are decreases. In delta modulation, bitrate and bandwidth are decreases. Now here encoder is 1-bit A to D converter. Now this is the bitrate RB, which is equal to 1 by Ts into n is 1, sampling rate. So the bitrate and bandwidth is decreased when compared with PCM and DPCM. Now that's why we go for the delta modulation. Okay. So now we'll see what is the operation and what are the problems we are facing in delta modulation. What about the error? Here error is almost uniform for all the quantization, but here error is less. Correlation between the samples are less. More number of samples are transmitted. Now here all samples are transmitted. Here difference between samples are transmitted. Now here is difference between the samples. So what about the quantization error? When there is only two quantization levels, plus delta minus delta, is an advantage or a disadvantage, which we will see. But this is the main difference between PCM, DPCM, delta modulation. Therefore, another name of delta modulation, which is nothing but 1-bit DPCM system. So here encoder and decoder is only 1 bit. Okay, no doubt. Now first we will see the transmitter and receiver portion. Delta modulation, transmitter and receiver, same. This is nothing but a DPCM system only, right? Now this is nothing but analog signal is going for sampling. Analog signal which is going for sampling. This is the sampled signal. Now this is the predicted signal, predicted sample value. Now this is the predictor. Now this difference is nothing but error, and that error is going for quantizer. Now here I will write in a different manner. Quantizer, this is E of NTS. We already the same diagram, right? Now this is the quantizer. Now this is plus delta and this is minus delta. When this difference is positive, is a plus delta, and this difference is negative, it is minus delta. Now this is error, this is the quantized error signal. Now this quantized error signal as a plus delta or a minus delta. This is plus delta or minus delta. Now this plus delta will be encoded as, this is 1 bit A to D converter. This is the encoder which is 1 bit A to D converter. Now this plus delta either binary 1 or binary 0. Now this predicted signal which is added, now this is the quantized error signal and this is the predictor output. Now these two are added. Now which is applied to the predictor, then this is the input to the prediction filter xq of NTS we are saying. And we already know the xq of NTS you are getting as the input to the predictor signal is nothing but the original sample value with some quantization error, you already know. Now here the thing is, now when this difference, now which is nothing but this is delta modulation, this is DM transmitter. First we will see the transmitter portion. Okay. Now what is the delta modulation transmitter? Now this is E of NTS. What is E of NTS? When this is E of NTS, which is nothing but x of NTS minus present sample value and a predicted sample value x cap of NTS. When this difference is positive, which means that now if E of NTS is positive or E of NTS is negative, when this is positive, it is quantized as EQ of NTS as plus delta, and it is encoded as increasing the delta value, right? Quantized plus delta, and it is encoded as binary 1. Now this is E of NTS is negative. Now this quantized error value as minus delta, now decreased by step size delta, and it is encoded as binary C. This delta is a step size, only two quantization levels here. Now see here, only in delta modulation, only two quantization levels. In delta modulation, only two quantization levels, whether it is plus delta or minus delta, incremented delta or decremented delta. Therefore, the number of quantization levels, which is equal to 2 power n, which is equal to 2 power 1. What is 1? Which is 1, which is nothing but 2, which is nothing but 1 is plus delta, another one is minus delta. One is incremented delta, another one is decremented delta. Only one level which is incrementing, another one is decrementing. Okay. So these are the two quantization levels. So more number of quantization levels, bitrate and bandwidth is increased. N is increasing. Because here less number of quantization level, therefore bitrate and bandwidth is decreases. But when it is incremented delta and when it is decremented delta, the incremented delta is nothing but when this difference is positive, decremented delta means this difference is negative. And it is incremented delta is encoded as binary 1, decremented delta it is encoded as binary 0. Okay, this is the delta modulation transmitter portion. Okay, now we'll see the receiver portion also. Now let us take here, this is a TS, 2TS, 3TS, 4TS, 5TS, 6TS, 7, at different just take a successive time difference between the samples. Right? Now these are the original signal. Therefore, this is x of NTS or samples of the original message signal. These are the samples. Okay. Now x cap of NTS is let us take, this is the staircase approximated signal. Let us take, this is the signal. Okay. Now let us take this signal. Now see here. Now this is more than this. Now x of e is greater than this. Therefore, this difference is definitely positive. Now it is quantized as plus delta. This is quantized as plus delta during this duration. Right? This is quantized as plus delta. It will maintain over a duration of Ts seconds. Now again at 2 Ts seconds. At 2 Ts seconds, this is the original sample value and this is the original sample signal strength and this is the staircase approximated signal or predictor output. Now this difference again, see here, this strength and this strength is positive again, then this is quantized as plus delta and again it is maintained as plus delta, right? Now see here, again at this particular position at 3 Ts seconds, now this strength and this strength, now x of t is greater than, so therefore this is positive and it is incremented by delta. Incremented by delta. Let us take increment and this is delta. Now at this particular position at 4 Ts, now this strength is more than this, right? This strength is more than this. Now this error is negative, then this is quantized as minus delta. Decremented by minus delta. Now see here again, at this particular duration, at this particular interval, now this strength is more than this, again this is positive, it is incremented by delta. Incremented by delta. Again, this is more than the required signal, so at this particular instant, now again this is decremented. Now again this is more than decremented. Decremented. Like this. Again this is incremented. Now this is the staircase approximated signal, which is nothing but x cap of NTS. The staircase approximated signal is nothing but predictor output. Okay. Now like this, now see here, you observe here, this is incremented delta, this is, let us assume, plus delta, plus delta, plus delta. Now decremented delta, incremented delta, decremented delta, incremented delta, like this. Now this is encoded as binary 1, 1, 1, 0, 1, 0, 0, 0, 1, like this. Now this is the deep delta modulation transmitter portion. Clear or not? Okay, now we'll see the reception, which is very easy. Hold on. Now this is the encoder output. Now therefore this is decoder. One bit D to A converter. Now this is a 1 bit D to A converter. Now see here. Now the output of the decoder is nothing but same. The quantized error signal. Now whether it should be in terms of plus delta or minus delta. So now this is a decoder output. Now we'll take the same help of this predictor. The predictor output is X cap of NTS. Now these are added here. X cap of NTS. Now what is X cap of NTS plus UQ of NTS, which is nothing but input to the predictor, am I not? Which is the input to the predictor. Now you already know that the input to the predictor is nothing but the original sample value plus some quantization error, means original sample value. Now that original sample value, now which is now this XQ of NTS, which is a input to the predictor, now which is applied to the low pass filter. Reconstructed filter. Now I'll take here, which is very easy manner here. Now see here. Now this is actually 1 1 1 0 1 1 0 1 at different time intervals. Now at TS seconds, this is binary 1, which means incremented by delta. At 2 TS seconds, now again binary 1 incremented by delta, 2 delta. At 3 TS, again binary 1 incremented by delta. At 4 TS, binary 0 decremented by delta, means 3 delta minus delta is now 2 delta. Now at 5 TS, again incremented by delta. Okay, 5 TS like this. Now 0 0 0 0, let us take. At 6 TS, again minus 0. At 6 TS, 0 means decremented by delta, means now at 7 TS, again 0, which is nothing but decremented by delta. Now the low pass filter, this binary 1, now this is ones and zeros. Now at the receiver, now the low pass filter output is nothing but this is the signal strength, right? Like this. So this is the signal which is X of t, which is a reconstructed signal which will be the output of the receiver. This is delta modulation receiver. This is the delta modulation receiver. This is the delta modulation transmitter. Clear or not? Now here only based on the two quantization levels, whether it is plus delta or minus delta. Okay. Now here the bitrate and bandwidth is decreased, and what are the other problems what we are facing in delta modulation also? We will see. Now first you note on this. Now for better understanding, you write here also 1, 1, 1, decrementing, 0, incrementing, 1, decrementing, decrementing. Now this is that. Now in delta modulation, this step size is calculated based on maximum slope of the message signal. Maximum slope of the message signal. In delta modulation, the step size is calculated based on maximum slope of the message signal. Therefore, now this is the reconstructed signal, right? X of NTS, X cap of NTS. Now what is the reconstructed signal slope? Now each signal, the successive sample difference is TS seconds. This is delta, 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 incrementing delta, or whether it should be decrementing delta, right? Now this is minus, this is incrementing delta, and this is decrementing delta. Now what is the slope of this reconstructed signal is slope of this is X cap of NTS. This is the reconstructed signal or staircase approximated signal. Now the slope of this reconstructed signal is or staircase approximated signal, which is y by x, right? Slope m, which is equal to y by x. So what is the slope here? Y is decrementing or incrementing delta, and x is over a duration of ts second. Now the slope of reconstructed signal is delta by ts. Now this is the slope of the reconstructed signal, delta by ts. Now this is the original message signal, or this is the analog signal. This is x of t, or these are the samples, or which is coming from here only, x of NTS, or this is the original message signal. We call it as m of t. This is m of t, and this is m of NTS. This is m of t, which is nothing but you can let as x of t. Now these are the samples, right? Now this is nothing but m of NTS, or similarly this is x of NTS, samples of this particular message signal or samples of this particular original signal. Now what is the slope of this message signal, which is nothing but change in y-axis by, this is continuously varying with respect to time, dm of t by dt, or dx of t by dt. This is the slope of message signal. This is the slope of message signal, and this is the slope of reconstructed signal. When these two slopes are same, when these two slopes are equal, you don't get any errors, right? Right. When these two slopes are equal like this, now this is the case 1. When these two slopes are same, when these two slopes are same, then you don't get any error, which means that the condition here is now delta by Ts, the slope of the staircase approximated signal, and the slope of the message signal, if both are same, now error which is equal to 0. When the slope of the reconstructed signal and the slope of the original message signal both are same, then you will get the 0 error, and you can get back the original message signal as it is, whatever we are transmitting, and receiver will be both are same. Okay. Hold on. Now you may take the condition here also with no error, or this is called as optimum step size. Now we will calculate optimum step size. But what is m of t, which is equal to am cos 2 pi fm into t. So the optimum step size is, now this is calculated based on maximum slope of the message signal, d by dt of m of t maximum. Your delta is calculated based on maximum slope of the message signal. Therefore, this is called as optimum step size, which is equal to differentiation of this differentiation of am cos 2 pi fm into t. Now this is the differentiation of am cos 2 pi fm into t, and this is the modulus, and this is the maximum value. Now which is nothing but the optimum step size by Ts, which is nothing but am 2 pi fm, differentiation of cos is minus sine 2 pi fm into t. This is the maximum value. So the optimum step size by Ts, which is equal to 2 pi fm into am. So the modulus is some minus value will become positive, and this is 1. So this is the optimum step size value without any error. Now see here, the optimum step size is calculated based on amplitude of the message signal, frequency of the message signal, and a sampling rate. Now, if the slope of the reconstructed signal, if the slope of the reconstructed signal is less than the slope of the original message signal, the staircase, all these cases I am explaining in that particular encoder. Now, which means that now the slope of the reconstructed signal or staircase approximated signal slope is less than the slope of the message signal, which is nothing but here the condition is if it is less than 2 pi fm into am. Now when these two slopes are not same, definitely error will occur. Now this error is called as slope over load distortion. This is the slope over load error. This is the slope overloading error because of because of small step size. Because of small step size. Now which means that now this is the original message signal, right? Now like this. Now this is the slope of the message signal. Now this is the slope of the reconstructed signal. Now this slope is less than this. Now definitely the errors will taking place. Okay. So this is the situation when the slope overload distortions will occur. Right. Now what should we do? This is the condition to occur slope overload distortion. Now to avoid slope overload error. Why the slope overload error will come? The slope overload error will come because of the smaller step size. So to avoid slope overload error, increase the step size. Your step size should be increased. So increase the step size. So if you increase this step size to the required levels, so if you increase these step sizes to the required level, then this slope overload distortions will be avoided. Okay. Now this is the condition to occur slope overload. In the examination he is asking, what is the condition to occur slope overload? What is the AM value to occur slope overload? What is the FM value to occur slope overload? And what is the AM value to avoid slope overload? What is the FM value to avoid slope overload? Like that the questions are asking. To occur slope overload, this condition should be satisfied. To avoid slope overload, this condition should be failed, means greater than. Situation is different. Now the reconstructed signal slope is now greater than the original message signal. Then again error will occur. Now this error is called as granular noise error, granular noise distortion. This is called as granular noise distortion. Now this granular noise distortion will occur because of larger step size. This granular noise distortion will occur because of larger step size. This granular noise distortion will occur because of larger step size. So now this is the slope of the reconstructed signal, which is greater than the slope of the original message signal. Now this type of errors will occur. Now this error is coming because of the larger step size. Now to avoid this error, to avoid granular noise distortion, to avoid granular noise distortion, decrease the step size. To avoid granular noise distortion, decrease the step size. To avoid this granular noise distortion, now the step size should be decreased. So actually this is coming because of the larger step size. Now you decrease the step size. such that this error will be overcome. So the examination is asking, to avoid granular noise, what should be the step size? To avoid slope overload, what is the step size? Without getting any error, what is the step size? Like that the questions are asking. Now, disadvantage of delta modulation. Now, let us take, this is a signal whose strength is varied from 0 volts to 10 volts. This is the message signal, okay? And let us take step size delta, which is equal to 10 volts, okay? Let us take step size delta, which is equal to 10 volts. Now there are a few samples you can take it. This is the few samples. Okay. Now let us assume at Ts seconds the original sample value. Let us take, this is at Ts seconds. Now the original sample value is, let us assume this is some 0.5 or something. This is a 0.5. Now this is x of nts. Now quantized sample value. Now x cap of nts, or this is the original sample value. Let us take, this is the quantized sample value. Now this 0.5 is a round off to some 1 volt. Okay, let us take, this is right. Now let us take, then after a few instants of time, like let us take some 70 seconds or something else. Now let us take, this is at 70s. This is some 9.2. Now this original sample value is going for the process of quantization. Now in our case, this is x of nts and this quantizer output. This is the quantizer output. What is the quantizer output? Quantizer sample value or quantizer output, which is EQ of, in our notation, EQ of nts. This is the quantizer output. Now in PCM, in DPCM, 0.5 nearest quantization level is 1 or something. Now 9.2 nearest quantization level is 10 or something. But here is only 2 quantization levels. In delta modulation, only 2 quantization levels, 2 power n, which is equal to 2 power 1, which is equal to 2, whether it is plus delta or whether it is minus delta. In this example, whether plus 10 volts or minus 10 volts. Which means this 0.5 is round off to either plus 10 volts or 9.2 is round off to 10 volts. Okay, or minus 10 volts, like this. Okay. Now what is the quantization error? The quantization error is nothing but a quantized sample value minus original sample value. Now see here the quantization error is 9.5. Here quantization error is 0.8. What you understand? What is your understanding? Now here this is a large error. This is a small error. Now the small error, now this is the large error. Now in delta modulation, there is a large quantization error is introduced for small amplitudes. The large quantization error, this is the large quantization error, this is the small. The large quantization error is introduced for small amplitudes. This is the small amplitudes. Now, there is a small quantization error introduced for large amplitudes. So, the delta modulation which is good for large amplitudes and introduce a large quantization error for small amplitudes, because here the delta modulation step size is